All right. Welcome back, everyone. Sorry, I'm a minute or two behind, but shouldn't be a big deal. Hope we've had a good week. Hope we're ready to dive back into chapter 4, where we left off in 4.4 last time. A couple of details. 4.3 is due today. 4.4 and 4.5, we will finish both those, so they're going to be due on the 11th. Test 3 is only going to cover 5 sections, arguably 4.1 through 4.5, but I'm not going to put anything from 4.3 in there. Kind of like I covered that material on the Riemann sum in class briefly, much briefer than anything else we've covered in this course, but then I didn't assign the homework, even though I accidentally said I did for a second, but then I corrected myself eventually. So while we did cover the idea of 4.3, I'm not going to test on it because those problems are just really long-winded and not the best technique for just an applied calculus course. It's great if we were going into numerical methods in a much heavier-handed world, but just not necessary for us. So it's better to use that stuff as an introduction to an idea and then move along from it. And you'd probably agree with the limit version of the derivative as well, but it's not as time-consuming to do those. So test 3 is going to cover 4.1 through 4.5, excluding 4.3. I will give more details in class next week. I'm still ironing out the details on that. It's been kind of a crazy week for me. But everybody's favorite phrase. This is a reminder that test 3 and the final exam are going to require a proctored environment. It doesn't mean you have to go somewhere to take the test. You can still just use this on your laptop, your desktop, whatever, but you will be required to have a webcam or a cell phone camera. So if you don't have access to one of those, then you will need to go somewhere that does. If you absolutely positively cannot handle that situation, you need to email me and see if we can work out something like you take it at on campus at TCC. That's usually what we have in those situations. The test will still be in my math lab. You'll just have to go through this lockdown browser. We'll see that in Canvas. I'm going to send you a link. I'm going to send you an email or post something in Canvas about how to use that. But I don't have everything organized yet. There will be a review in my math lab. I'm going to make sure that that's available tonight if it is not already. I don't remember off the top of my head if I had that available, because I know I still need to post the updated homework due dates. Oh yeah, this new laptop is weird. I had to get a new laptop after that. What was it, like 3 weeks ago? Everything went crazy on us and I was like 20 minutes late for class. Yep. Let's see. Is the review already up? I feel like I already had them up by default. Yes, it is 4.1 through 4.5. So you do have your review available. I just haven't updated the homework due dates for 4.4, 4.5, but they will be updated later this evening, as we already saw here, the 11th, since we'll finish those today. We will also start 4.6 today, but we won't finish it. That's a pretty lengthy section to discuss. What do I want to say? So test 3 is likely going to be the 12th through the 14th. Since I'm going to be talking about it next class, I don't want to say that you have the 11th to take it. If this is a problem that someone cannot take it the 12th, 13th, or 14th, if you absolutely need to take it on the 11th, then email me and let me know, or let me know during class in the chat window, and we can work out something different. I can make it available on the 11th, but I just would hope that most people would take it the 12th, 13th, or 14th. A, gives you an extra day to study, and B, it will give you time to see, what's going to be the what exactly you have to do to get through the lockdown browser, whether you're starting in Canvas and using a link there, starting in my math lab and using a link there, whatever the situation might be. This is actually the first time I've had to do this, so that's why I am waiting to figure it out. I've got to do the training. So that being said, let's go ahead and pick up where we left off at the very, very, very end of that last section where we were talking about how to find the average function value through integration. It was a really cool method. We had that formula here where you can kind of see it, that you saw the derivation of it, where you integrate the function over a to b, and then you divide by the length of the area, the width of the area, however you want to say that, b minus a. And this was the formula for our average function value. So we're going to do one example with that really quickly. You're going to see me have to start and stop the videos a little more tonight. Not that that's a big deal, but you'll just, yeah. All right, so let's go ahead and get into it. As always, if you have any questions, hit me up in the chat.
I'll write the formula one last time just so you see it. The average from A to B is equal to 1 over b minus a integral a to b f of x dx. That's our formula. Leading us to our example, which we are up to, I think, 5? Yes, 5. Let us find the average value of f of x equals 3x squared. We'll go with a simple function on the window 0 to 4. See, finding an average value when you have finite values, oh, you got elements of 1, 2, 9, and 12. Add them up, divide by the number of things you had. That's what this is similar to, but functions are continuous. It's not just elements at 1, 2, 3, and 4. It's elements at 1.1. It's elements at 1.09. It's elements at 1.03, 09, 05, 04, 31, 26, 8, 8, 8, 3, 9. You don't want to have to add up infinitely many elements and divide by, in theory, infinity. Fortunately, we have this formula. So the average value from 0 to 4 should be equal to 1 over 4 minus 0 times the integral from 0 to 4 of 3x squared dx. Like I said, if you want to put the 4 minus 0 in the bottom of the integral, you can. It's just different notation. It's going to end up being out front anyways, so why not do it this way? That's 1/4 times the integral from 0 to 4 of 3x squared dx, which is 1/4 times the integral from, I'm sorry, no more integral symbol. So I'm about to integrate. This is a polynomial term. Add one of the exponent, divide by the same, leave the 3, so times 3. Adding one of the exponent makes it a third, dividing by the same value. I don't need a plus c because we're going from 0 to 4. Let's clean this up. 3's cancel. That's 1/4 x cubed from 0 to 4. So that's 1/4 times 4 cubed minus 1/4 times 0 cubed. 0 cubed is 0, so there's no subtraction. You could cancel one of these 4 and just say that's 4 squared, or you can say 4 cubed is 64. 64 divided by 4 is 16, which is also 4 squared. So we get 16. Let's graph that function. What was it? 3x squared, 3x squared. We're going from 0 to 4. Let's just do the window, x min 0, x max 4. And we don't have enough of that, so let's change the y window. We don't need any negatives. Let's go from 0 to, if you actually plug in 4, 4 squared is 16. 16 times 3 is 48. Let's just make it 50 to be safe. I don't know why I made the y minimum that, but I said I was going to make it 0. Oh, I tried to type 0 and it didn't overwrite it. There we go. Trace. What's f of 0? It's 0, because 0 squared is 0. What's f of 1? It's 3. What's f of 2? It's 12. What's f of 3? It's 27. What's f of 4? It's 48. And if you added up those 5 values, 0, 1, 2, 3, and 4, and divided by 5, you would have an average of 5 finite points of the function. And it's probably in the ballpark of 16. Let's see what it was. It was 0 plus 3 plus 12 plus 3 squared is 9, 27 plus 4 squared is 16, that's 48. If you divide that by 5, you get 18. So if I just average those 5 points, you get 18. But this is a continuous function. We're not just including the whole numbers, we're including 1.1. So, oh, what is it at 1.1? It's 3.63, so you'd have to add that and divide by 6. So what is going on at 2.957? I mean, you would be doing this for the rest of your life, and I put a plus sign in there, which is why it gave me a syntax error. But the point being, you would never be able to calculate those infinitely many values, add them up, and divide by it. Fortunately, the calculus saves our butt thanks to laws of averages, just kind of shifting an area, changing the shape into something we can relate to, and setting them equal to each other. Gives us a quite easy formula. So if you averaged those infinitely many heights from x equals 0 to x equals 4, you'd get 16.
And that'll be it for the average value theorem. All right, so that finished out 4.4. So now we're going to spend a decent amount of time doing 4.5. Like I said, this is going to be parsed out in a couple of videos, not a big deal. We'll still take our break about halfway through per usual. Let's go ahead and get 4.5.
Integration by substitution. So we know how to integrate certain functions. In particular, but not limited to, we know how to integrate a power rule, as long as n is not 1. We know how to integrate e to the x and its variations. Again, I'm not writing down every single one. I'm not writing down the answers. I'm just saying what we know how to integrate. We know how to integrate 1 over x, which is when it is, which was the first one, but when it is 1. Let me make sure I give myself lots of space. Pardon me. But we don't have the same basic rules as with derivatives. Products, quotients, etc. There is no product rule. There is no chain rule. There is no quotient rule. Etc. etc. For integration. You can take a derivative of pretty much anything. That's not true of integration, though. The math behind integration is a little weirder. We've already seen how it can be weird, particularly the whole, oh, you can't let the n be -1 in this case because then you end up dividing by 0. So we had this other case that ended up leading to the natural log of an absolute value. So the math behind integration's a little weirder. I mean, just the whole setup, having to integrate infinitely many rectangles using those differentials, the dx's and all that stuff. And it gets even weirder when you try and say, oh, well, the product rule is this, the quotient rule is that. Well, no, they really don't exist. When you have a product, instead of having just one flat rule, for a formula, you have several different techniques that you would need to try. And even after you try all those techniques, you're not guaranteed an answer. And I will even show you ultimately, not today, an integration that we don't even know how to do as a class. I'm not saying it can't be done. It can be, but you can't do it with any traditional calculus methods. You actually have to use a statistics trick, oddly enough, but not for us. So what do we do? Because we're going to start integrating products and quotients and things that look like chains. Well, our first technique is integration by substitution. So to get around this, option 1, and this is generally written as option 1 because it's the first thing you should probably try, is using a substitution. Sorry, I just keep thinking in the back of my head, man, I hope this records. It's half of what I can think right now, on top of something else going on in my life that is the reason I have to cut class early. Sorry, I'm frazzled. Okay, so option 1 is using a substitution. Now, we've done substitutions before. Back when we wanted to do something, we called it in quadratic form, like factoring x to the 4th plus 3x squared plus 2. We'd call that in quadratic form, and we'd say, let u equal x squared, the middle variable term. After you'd say let u equal the x squared, you'd have to make an extra statement, and you'd say, well, if u is x squared, then u squared is x to the 4th. That way you could transform your variables from x's to u's and get something in a different space, is what we call it, a different variable space, but a lot easier to process. That's what we're trying to do here. We're trying to use some substitution to make something that's ugly, turning into something that's not ugly and is processable with one of our formulas. So, point being, that quadratic substitution thing that I mentioned, there were 2 substitutions, but they kind of one came from the other. That's the same idea here. So this is going to require 2 substitutions. First, we will say u equal, and then whatever, squiggly, squiggly, squiggly. That just means whatever you're going to say let u equal. Maybe it's 2x, maybe it's 5x squared plus 17x minus 3. U equals, then your choice. But it's not really a choice necessarily. By choice, I mean there's really only one good choice. Then take its derivative, but it has to be in this form. Du dx. You have to write it this way. You cannot write u prime. You cannot write f prime. It has to be written as du dx. Just trust me. And this is something that we're going to do over and 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 over. Okay. So take the derivative and multiply both sides by dx. This is an algebraic step that I have referenced before, where the du dx, while it's technically not a fraction, there are a lot of ways that we can treat it as a fraction. Because if this is a fraction, you'd say, oh, the d's cancel. But the d's don't represent a variable. They represent the differential, a small change in the horizontal versus a small change in the vertical. That's what they really represent. So we're going to take this thing du over dx equals, say, 2x maybe, or 2u or 2z, whatever it might be, and you multiply both sides by dx. So we are going to split up this thing as a fraction. But the du is its own thing, the dx is its own thing. Don't think of the d and the u or the d and the x as separate entities. They're not. Du is thing 1, dx is thing 2. So we're just clearing the fraction, basically. So we multiply both sides by dx. Finally, divide both sides by whatever is next to dx now. So in other words, you have taken what was du over dx and you've solved for dx. That is what we have done. Again, I'm just giving you the steps. We'll apply this very shortly. At this point, we can substitute u and dx into the original integrand, integral, however you want to say it, antiderivative. Now, hopefully, have something that's easy to integrate as long as you only see u's. In other words, no x's. But this is the classic substitution problem. This is the classic, I give you a problem in the dollar and you find the answer in yen, but I go, no sir, no ma'am, I want the answer as a dollar, you gotta go back. So after integrating, and again, the integration should be simple, go back to x as a variable. Now you don't have to use the letter u, you can use the letter y if you prefer. So then you'd say, we'll let y equals blah, 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 and then its derivative would be dy over dx. And then you'd only see y's when you go to integrate. The reason we like the letter u is the word substitution. Well, the second letter is u. We don't like the letter s because it looks like 5. Excuse me. So example 1. We're not actually going to do any integration here. We're just going to practice the substitution stuff. So find the differential du. Sorry, find the differential, which means the derivative, du, then find dx. That was weird. Why did that go back? And then the third strike is my technology's been a little weird, besides just Zoom not recording. I was using Excel in my last class and it kept, I don't even know how to say it, it just kept messing up really badly. All right, so A. We're going to let u be 5x to the 4th. So our goal is to find the derivative and then break up its differentials, ultimately solving for dx. Our goal is to take this, take its derivative, solve it for dx. We have our let u equals, you take its derivative, and then you solve for dx. Okay. So take the derivative. Du dx. This is a straight up power rule. So drop the 4 out front, so that's 5 times 4 times x to the 3rd, decrease the exponent by 1. You might be saying, well, why aren't you adding 1? Why aren't you dividing by the 5 or the 4 or whatever? Because this is a derivative, not an integral. Here's what's funny. To do some integrations, you have to do a derivative to get to the integration part. 5 times 4 is 20, so we get du over dx is equal to 20 times x to the 3rd. So that's the derivative. Now what I'm going to do is I'm going to take that du over dx equals 20x to the 3rd. And I am trying to solve this thing for dx. It is a thing that is currently in the bottom, which you have been through algebra classes that taught you how to solve for things in the bottom. You clear the fractions and then divide the rest out. So we got to multiply both sides by dx. Actually, I guess this one should just be. There we go. So multiply both sides by dx. That's the step I didn't even ask you to do linear algebra. I told you what to do. Take its derivative, multiply both sides by dx. That's what we just did. We just did this step. Then divide both sides by the thing that's next to the dx. And again, I don't have to tell you this. This is purely algebra 1, algebra 2, arguably. So now what we have is the dx's cancel to get du is equal to 20x cubed dx. See, the d's don't cancel. The dx counts as something and the dx counts as something. Those will cancel that way, but it's not just a d canceling with a d. That's not what it is. So now we're trying to solve for dx. How do we solve for something that multiplies? Divide it out. Divide by the 20x cubed. And again, I literally wrote the step. Divide by everything else on its side. So that the 20x cubes cancel there. And what we get is du over 20x to the third is equal to dx. This is the answer for this problem. We have done no actual integrations, excuse me. This isn't a real full problem. This is just practice. All right, let's do another. B. And this one's going to be u equals, let's mix it up a little, e to the 5x, then a minus 7. So let's take its derivative, du dx. E to the 5x, you've got to chain rule that. So it's the derivative of the inside times the whole thing, because it's an exponential. The derivative of an exponential is the derivative of the inside times itself. Old rule. So the derivative of the 5x is the 5, and then you leave the e to the 5x alone. Again, that is an old rule. If you're rusty with it, go practice 20 of them. Go back to the notes. Look at your formulas. The derivative of 7 is 0. It's not minus 7x. Remember, we're doing derivatives. We're going the other way from what we've been doing lately. So the derivative of minus 7 is nothing. This is the derivative. So now what we're going to do is we're going to multiply both sides by dx. There's nothing to clean up. So let's take our du over dx equals 5 e to the 5x. And we multiply both sides by dx to clear the fraction, which will give us du is equal to 5 e to the 5x dx. And then we're solving for dx. That's what we're solving for, so we got to divide everything else out. So we divide both sides by 5 e to the 5x. So that jazz cancels, telling us an answer of du over 5 e to the 5x is equal to dx. These are known as differentials. When you have them separated as a du over here and a dx over there, we start thinking of them more as differentials. Again, we've discussed how dx is the width of those infinitely small rectangles when we talk about integration. When we talk about derivatives, we say that dx is the change in the horizontal position. But the point being that when we talk about a dx, we're talking about something that's going to 0. It's going to be the smallest thing imaginable relative to the du or dy or whatever it is. So again, this is just the substitution part, the second part of the substitution where you figure out what your substitution is, you take its derivative, and you solve for the dx differential. So with that said, let's try out example 2, which will be to find the integrate by substitution. So let's again look at this process as a whole. We'll say let u equal something. I haven't told you what to let u equal. because we're going to do it right and then we're going to do it wrong. So once you figure out what you have your u is, you take its derivative and solve it for dx. Okay, so for a, 2a, we got the integral, parentheses, x squared plus 3, closed, raised to the 4th power, times 2x dx. So what we have to do is come up with a substitution, because this is a product. This is like a A times a B. And we said earlier, there is no product rule for integration. Also, it kind of looks like you have to chain this. You got an inside bit with an outside bit. Well, there's no chain rule for integration. Fortunately, this is all going to fold into itself with our substitution. So we're going to try a substitution. And I'm going to go ahead and give you a big hint. The substitution is usually the inside or bottom, and possibly just the inside of the bottom. Well, there's no bottom of this, so it's clearly not that. Hint, the substitution is usually the inside. I'll give you a better declaration of that later, but not yet. I don't want to spoil too much of the fun. So what's the inside? Well, the 2x is definitely not that. This looks like the part that has an inside and an outside. The x squared plus 3 being the inside. We've talked about insides and outsides previously for chain ruling. So we're going to say, I don't know why I wrote it over there. Let u equal the inside, the x squared plus 3. So that's the substitution I've chosen to do. So when we say let u be that thing, now we take its derivative. We go du dx. And again, you need to use this notation because you have to see the differentials because you're going to split them up. Well, the derivative of x squared is 2x. The derivative of 3 is nothing. Again, this is a derivative, not an integration. Don't add 1 to the exponents, you're subtracting 1 to the exponents. And then we got to take this thing and we got to solve it for dx, the thing in the bottom. And I will admit this is not the only technique for this. There are other techniques, but unfortunately, they require a little bit more vision, a little bit more forethought. And I don't think that that technique is the best to be doing in an applied calculus class. If this was an advanced, more science-based calculus class, I like that technique. I'm not teaching in here though, because it's more guesswork. This right here, what we're doing is definitive. So we're solving for dx. So, well, first we have to multiply both sides by it. So we have our du over dx equals 2x. We multiply both sides by the dx. Whatever you do to one side, do to the other. That way the dx's are gone on that side. So now what we have is du is equal to 2x dx. Now again, we're trying to solve for the dx. This is what we're trying to solve for because that's what I've suggested so far. We haven't really seen why, but we'll see it soon enough. So we're going to have to divide both sides by the 2x. So that they're gone there. And the dx is now solved for. So I'll leave it in red. Du over 2x is equal to dx. This is a major relationship between how the width is changing in comparison to how the height is changing. So if you know the x value, you can take whatever your change in height is divided by twice your x position, and that's how far the x position should be changing. That's kind of a weird way to think of it. Usually you'd rather want the du to be solved, so your change in height is 2 times the x position times the change in the x. This is a little more sensible, even though you might have a hard time grasping it right now. This has a point though. So now what are we doing? Where is it up here? At this point, you can substitute u and dx into the original integrand. U and dx. So we're going to write a u wherever you had x squared plus 3 previously, and we're going to write du over 2x wherever we saw dx previously. Those are the things that are getting substituted. So right here, we had x squared plus 3. We don't want that anymore. We now want to write that as a u. And then this dx right here, we don't want that anymore. We want this because that's what dx is equivalent to. Now you might say, well, you're not plugging anything in for the 2x. You are correct. The secondary method I mentioned that's a little more forethought requiring, you just try and manipulate these things to match for the du equals, but they don't always match and the manipulation can be tough. But by solving for dx here, this 2x, or at least the x, should go away. At the end of this next step, there should be no more x's. That is the whole point. You can have numbers, you can have u's, but you can't have x's anymore. We're going from the dollar to only seeing yen, and the dollar is the x, the u is the yen. So let me undo all those little circles I had. Okay. So now our integral. Now I'll write this out. The integral of x squared plus 3 raised to the 4th times 2x, missed my x, dx. This will become the integral of, instead of writing x squared plus 3, we write u. Again, this x squared plus 3 is u, so write it as a u. But it has a 4th power, so don't forget that. So the 4th is still there, times the 2x is still there, but I'm replacing the dx. The dx is really this, du over 2x. So times du over 2x. This is important because we still have a differential, and now the differential is in our new variable. You can't have a bunch of x's here and then a u here, or a bunch of u's here and an x here. We're only supposed to have a single variable for integration, ... for now. So what happens? Well, we can clean this up. The u to the 4th is just a u to the 4th. But look at this 2x right here, and this 2x right here, they're identical, top and bottom. They cancel. Gone, gone. Now again, the 2's don't necessarily have to go. What's absolutely important is that the x's are gone, and all you have are u's and du's. So this is now just the integration of u to the 4th du. Look how simple that is in comparison to the original problem. It looks like a D4, I'm gonna fix that. But just look at the comparison of those two examples. They're mind-blowingly different. Oh, that's even worse. Maybe not worse, but there we go. My D is ugly. I'm hyper-focused right now, sorry. So there we go. The integration of u to the 4th times du. Well, that's just a straight up power rule. So we add 1 and divide by the same. Now remember, when you integrate, you don't use this symbol anymore. You don't leave the du anymore. All that stuff is gone. When you go to apply your formulas, u to the 4th changes to u to the 5th. Divide by 5. This is an integration. You're adding 1 and dividing by that number, not bringing the exponent down and decreasing it by 1. So in this integration problem, you had to do a derivative and an integral. This is one of my favorite styles of problems because of that. It puts everything all together in one nice, neat package. And if you box this up, first of all, you're wrong because there were no upper and lower limits, so you got to have your plus c. Second of all, I gave you a problem in dollars, and if you give me this as your answer, that's in yen. I don't want the answer in yen. I want it in dollars. So we have to go back to x. How do we go back to x? Well, instead of writing u, we write what u is equivalent to. We said u is equivalent to x squared plus 3. We made that choice. We made it based on the problem, but we made a choice. So when all is said and done, this is now equal to the integral of, instead of writing u to the 5th, it's this thing to the 5th. So we'll need a parentheses. X squared plus 3 raised to the 5th power all over 5. What did I do wrong? I did it intentionally. That's right. I left my integration symbol. See, I deleted it here and I brought it back here. It's very easy to just think that's going to be in the answer. So we got to start over. No integration symbol. It's just the u to the 5th should be x squared plus 3 raised to the 5th all over the 5, then plus c. This is the answer in all its glory. Or if you like your fractions separated, 1/5 parentheses x squared plus 3 to the 5th, then your plus c. That would also be acceptable. I think the first version looks a little prettier, so that's how I usually do it. But there's nothing wrong with the second version, so you do you. Again, this is a lovely problem because it involves both of the major techniques we focus on in this course. Limits were important to getting to derivatives, and limits are important for going to an integration because you make those triangles, you take the limit as the width goes to 0. But we really don't focus on the limit aspect so much as the application of the formulas of integration and derivation, differentiation. So this was the correct substitution. Let's do this problem again, but let's see what happens with a wrong substitution. So why is it important to do this? Well, maybe when you're taking a test or doing a homework problem, you make a wrong substitution. How can you tell it's wrong? Remember, the main point was to get this right here, an integration with no x's. You got to be completely in your new chosen variable. So let's go back to the original problem, x squared plus 3 raised to the 4th times 2x dx. So instead of letting it be the inside, let's let it be this thing to the side. So let's say I said, let u equal 2x. Now, another substitution you might say is let u be the x squared plus 3 to the 4th. First of all, it's generally not that complicated. It's usually not the inside and the outer exponent. So that's just a big spoiler for you. But again, there is a third substitution that you could try that would fail. I'm just doing the second one. If u is 2x, when you take its derivative, it's just 2. You're going to multiply both sides by dx. Excuse me. Which will give you du equals 2 dx. You will divide both sides by 2 to solve for the dx. So you get du over 2 is equal to dx. Okay, so our integration of x squared plus 3 raised to the 4th times 2x dx is going to become, well, the first bit, this x squared plus 3, I didn't see anything about that over there, so we have to leave it alone, including its 4th power. U, we said, was 2x, so this thing right here, that's going to be our u. So that's times a u. And then the dx we just said is over here. Dx is now du over 2. So this is times du over 2. All right, well, that 2 doesn't cancel like it did in the last example. That's not a problem, though. Again, just constants aren't really issues. It's the variables. You have x's in here and a u and a du out here. There's no way to proceed with this. There's still mixed variables and absolutely no way to get rid of them right now. So this is how you can tell that you've gone wrong on your substitution process. And again, my major hint was that your substitution is usually the inside of something or the bottom of something, or if the bottom has an exponent, the inside of the bottom. I'm not telling you it's that way every time. There are more complicated problems in the world. What I'm telling you is that's what we usually see. All right. With that being said, let's do one more of these, and that might be all the time we have, given my emergency situation. So let's do the integration of x to the 4th plus 5 raised to the 8th power times x cubed dx. So again, this looks like a product rule. It could look like a quotient rule. We'll see. We will see an example of that next class. But it looks like a product rule, and there's no product rule integration formula. Not for us. We have methods for them. The first being this substitution technique. Another technique is known as integration by parts, and it'll be a minute before we get to that. And by minute, I'm exaggerating. So when we look at this, you go, all right, well, Mr. Beckner said the substitution is usually the inside. This is the inside, so that's probably what the substitution is. Now, what you might accidentally do is just say, let it be the part that's the x to the 4th. That's not going to be good enough. You will actually get something that only has u's. But the integration will still have what looks like a chain rule effect, and it won't be good enough. So let's say let u not be just the x to the 4th. It needs to be the x to the 4th plus 5. Try out just having it be x to the 4th. You won't get the same answer. So we take that and we take its derivative. So du over dx is equal to, not 3, excuse me, I'm talking and writing at different speeds. 4x to the 3rd would be the derivative of the x to the 4th. Derivative of 5 is nothing. And then we take this bad boy and we solve it for dx. So du over dx equals 4x cubed. Same 2 steps every time pretty much. Multiply by dx so that those cancel, giving us du equals 4x cubed dx. Divide both sides by the stuff that's not dx on its side. 4x cubed, 4x cubed, so that those cancel, giving us du over 4x cubed is equal to dx. So again, in terms of what's important for the substitution, it's the let statement. We're going to rewrite the x to the 4th plus 5 as a u, and the dx statement. So our original integral, x to the 4th plus 5 raised to the 8th times x cubed dx. This will become the integral of, instead of writing x to the 4th plus 5, I'm going to write u. But we leave the exponent of an 8 there. The x cubed after that is also going to stay. And you're like, oh, we're mixing variables here, but just hold on a second. Now the dx gets replaced. The dx is du over 4x cubed. So times du over 4x to the 3rd. Bad looking x, just fixing that. There we go. And look at this. We have an x to the 3rd in the top. We have an x to the 3rd in the bottom. The x to the 3rds cancel. I don't want to show the crossing out this time. I want to leave that there. So this becomes the integral of u to the 8th times du. The u to the 8th is in the top. The du is in the top. This 4 is still here. It's in the bottom, though. So make sure you put it in a bottom. this no longer has any x's. That means we have done an appropriate substitution. When you integrate u to the 8th, you get u to the 9th over 9. So this would be u to the 9th. When we integrate, we're adding 1 for power rules over 9. But then there's that times 1/4. Now, you might not put the 1 there. You may just leave the 4 in the bottom. It's up to you. And then you have your plus c. But this 4 was in a denominator, so it needs to be in a denominator somewhere as a product. What some people may have done is taken the 4 out. Like this, 1/4 integral of u to the 8th du, which would give us 1/4 times u to the 9th over 9 plus c. The same thing, just in a different order. The 4s and the 9s are in the bottom, so you can multiply them to get 36. So that's 1 over 36 times u to the 9th, or u to the 9th in the top, and 36 in the bottom, plus c. Well, we have to go back to x. Instead of writing u, we write x to the 4th plus 5, because that's what u is equivalent to. That's what we said. So instead of u to the 9th, it's now x to the 4th plus 5 raised to the 9th over 36 plus c. And there are a couple different algebraic ways to write that, but that's, in my opinion, the best. And if you don't trust this, you can take the derivative of the answer, and you should get the original problem. You will need the chain rule, because these have insides and outsides. Insides and outsides, that's pretty typical when you integrate by substitution. You usually get something that if you were going to take the derivative of this, you'd have to chain it. It's kind of interesting in that manner. If you took the derivative of this, the 9 would go out front, the 9 would reduce with the 36 and give you a 4 in the bottom. This would be raised to the 8th power, but then you got to multiply by the derivative of the inside. The derivative of x to the 4th plus 5 is 4x to the 3rd. That 4 would cancel with the 4 that's in the bottom, and you have your x to the 3rd to the side. It does, in fact, work. What I think is super interesting about this process is that's too low. There we go. If you try to do the integral of x to the 4th plus 5 raised to the 8th power, this can't be done this way or any easier way. What I think is interesting about this is, what am I missing? What's different about this versus the original problem? The original problem had this x cubed in it. It actually made it look worse. With that x to the 3rd, you go, oh man, that looks way uglier. It looks like a product rule. This doesn't look like a product rule. This should be easy. Actually, no. That's what is really, really funny about this, is that you need that x cubed there, because in this substitution process, you end up with an x cubed in the bottom of your dx that will cancel it. Because when you go to try and do a substitution here, you'll still have that x cubed in the bottom, but it's not going to cancel with an x cubed in this top. Now you've got an x cubed in the bottom and a u in the top, and you can't integrate it. What you would actually have to do with this problem is take that binomial and multiply it by itself 8 times, which is probably going to take you like 30 minutes to do, and then use the power rule. Again, the point being, the uglier problems are often actually easier to do than their simpler looking counterparts. So again, I'm not saying this can't be done. I'm saying it can't be done this way. I mean, that would be a lot of products to have to do. A lot of products. Oh man, I'm telling you, 30 minutes, I might actually being generous there. It might be 40 minutes for you. I don't know. It might be. It depends on how quick you can go, but it's a lot of bookkeeping. How are we on time? It's also important that this x cubed is x cubed, and it's not an x squared, and it's not an x to the fourth. There's a relationship between this and this when you're dealing with polynomials. Notice that this was an x to the fourth, and this was an x to the third. That relationship right there, the fact that they're one off from each other, is important because when you do the derivative of the inside ends up bleeding to an x to the third. You end up dividing it to a bottom, and that's how we end up matching that power and canceling it. So let's say this number right here, let's say this was a 7, you couldn't do it as a substitution. Let's say it was a 6, you couldn't do it as a substitution. Let's say it was a 2, you couldn't do it as a substitution. When you're dealing with polynomial terms, and this is critical, the biggest exponent inside and the exponent outside, generally speaking, need to be one off from each other. This needs to be one less than the other. That way the derivative part will cancel it. Go back to example A. Look at this. This was an x squared, and then this was an x. It has nothing to do with the outer exponent. The outer exponent is not consequential to the substitution. But this was a 2 and this was a 1. In other words, if this was, say, a 7 right here, I would need this to be an x to the 6th. Now, if there's extra terms and extra variables, that could complicate things, or they could be set up nice and pretty, which I'll have an example of for next class. So what I'd like you to do for now is, before we, yeah, I don't know that I have enough time to do this one because I need to be out the door in 5 minutes. Think about this. The integral, one of these is going to be example C. The integral of x e to the x squared dx. Now, the fact that the x is in the front instead of the back like the last two, that doesn't matter. If you think you need to put the x after the e to the x squared, that's okay, but it really doesn't matter that it's in front if this is the proper one, versus the integral of e to the x squared dx. One of these you can evaluate, the other you cannot, using this technique. And in fact, the other one is very similar to that thing I mentioned, needing a statistics trick. Maybe there's a negative involved, maybe there's a half involved. It has to do with something called the normal distribution. But that's not anything we're doing in here, so don't worry about that. But just using those first two examples, I'm not going to assign the homework for this section officially yet because we're not even close to being done. But try and do these on your own using a substitution, and I hope it's obvious which one actually works.
And obviously you're not going to have enough time to figure that out since I'm not out the door in 5 minutes, as I said a minute ago in the video, but that should be obvious. So let's go ahead and get the next segment set up. All right, so we're going to get into the one of those now that does in fact work.
Both of those. Let's pick up where we left off, which was 4.5, the substitution technique. So we said we need the substitution technique at times because there's no product rule, there's no quotient rule, there's no chain rule for integration, whereas we have these things for derivation. In fact, not all functions are integratable or anti-differentiable under normal rules. Sometimes you have to just go to complete numerical analysis, or sometimes you have to use these weird fancy techniques that they teach you in grad schools. And after that, integration is a much more complicated idea than derivations, than derivatives. And we did some examples. We talked about how you have to make a let u statement, kind of like you did back in pre-calc to change variables over. But then there's a couple extra steps. You had to take its derivative. You had to use the differential form, the du over dx. The du and dx are differentials independently. Then you multiplied both sides by dx. We start trying to treat this like a fraction, and then divide by whatever's next to the dx. Those two last steps are just basic linear algebra that everyone should know how to do. It just looks a little ugly. So the two things you need to have are a u equals and a dx equals. You plug those two into your original integrand, your original integration. And if everything works appropriately, if you did the right substitution and substitution was the appropriate technique, you will notice that all the x's go away. You may be stuck with an extra ugly constant, but these things boil down to something much simpler, like this ugly integral turned into the integral of u to the fourth. And this ugly integral with an appropriate substitution turned into the integral of u to the eighth over 4. Oh no, over 4. That's terrible. Sarcasm. And then we just have to remember that after we integrate, we go back to our original variable. Go back to the original variable. And then I also pointed out that what's interesting is you might say, okay, well, if we can integrate this x squared plus 3 all raised to the 4 times 2x, you could probably do it if the 2x wasn't there. And in fact, we don't know how to handle that yet. Well, I did say that you could expand this thing to the 4th power, but that's kind of a pain. Nobody wants to have to do that. And then the same thing goes for this one. Without that x cubed, this would be a massive pain in the butt to have to do. And that's the one I think I said would take you probably a half an hour plus. And you got to have really good bookkeeping skills to even still get it right. So what's interesting is you might have the parentheses part, but you're missing this part, and then you can't actually integrate it. Now, I'm not going to give you those problems, but they do exist. So the last thing we did was I said, well, think about this one versus that one. The left one's uglier than the right one, but in fact, because this x is down here, it makes it a prime candidate for substitution because the variable that you'd be doing your substitution on, this x squared, the inside part, generally speaking, you can also say that with polynomials, it's generally the higher power part. Because this is 1 degree lower, that means when you solve for the dx and plug it in, it'll cancel this x out. Whereas in this format, that doesn't happen. And this is one of the classic first examples of an integrand you can't do, well, classically. What's the term? Sorry, I blanked for a second. I was thinking about something else. Transcendental functions. So when we talk about transcendental functions, they're the things that we're used to dealing with basically. And then we can integrate this type, but not this type, even though it looks simpler. Just kind of interesting. So that was the spoilers. You can do the left, but not the right. And the next example we're going to do is the one on the left. So for C, and under orange, I want to stick with red. Also, I'm using only one hand today, and that's probably going to be true for the rest of the semester. I've been dealing with a pretty bad injury, and it's just getting worse, and my right arm is not really very good right now. So it's fun using a mouse with your left hand. Good thing is, I am actually left-handed, so it doesn't affect my writing ability. You might say, well, you probably should have been right-handed with that terrible handwriting, and I'd say that's a great joke. I've made it myself. But I don't really have much experience using a mouse with my left hand. But anyways, we're not going to let that get us down. We're going to keep going on. So the integral of x e to the x squared dx. And I pointed out last time, the x could be behind it. This would be the same thing as if the x, instead of being in the front, was behind it. So you've got what feels like a product rule, so we probably need to say let u equals, and I was supposed to do that in black. The problems are supposed to be in black. Red is for the writing. Third tie is the charm. Integral x e to the x squared dx. There we go. So we say let u equal, and I said it's generally the inside, or if you're dealing with a bunch of different polynomials that are all over the place, you usually want it to be the higher order polynomial part. So it's definitely the x squared. If you say let u equals x, you're going to very quickly find out that nothing works. Then you take its derivative, but you have to do it in the form du dx. If you don't like the letter u for substitution, the second letter of sub, you can use y or z or whatever you like. The derivative of x squared is 2x. We multiply both sides by the dx, so we get multiply both sides by dx to cancel the 1 in the bottom. So that'll give us du equals 2x dx. And then we're going to divide both sides by the 2x because we're supposed to be solving the 2x, writing and talking. Divide by 2x because we're supposed to be solving for dx. And what that gives us, finally, is that du over 2x is equal to dx. And it is this that we have to plug in along with this. Instead of the x squared, we'll write u. Instead of the dx, we'll write du over 2x. So this integration is going to become the integral. Now I'm not changing the x stays for now. The e to the x squared part is what I'm going to change to u. And then the dx is changing to the du over 2x. And I'll do blue what I changed. So the x squared turned into a u, and the dx turns into du over 2x. Now the 2 doesn't cancel, but the x's do. This x cancels with this x, which is exactly what you need to see. So this is the integral of e to the u over 2 du. Or you can pull that 2 out of the integration. 1/2 integral of e to the u du. This is a super simple formula. The integral of e to the u is e to the u. So this is equal to 1/2 e to the u, but don't forget your plus c because there were no upper and lower limits. But then we have to go back. So instead of writing u, we write x squared. So this is equal to 1/2 e to the x squared plus c. That's our answer. All right. Now, like I said, I'm going to go a little quicker here. I might talk a little quicker. I've got a lot going on, and I'm barely able to even cram this into my schedule, but got to do what we got to do. The cool thing is, if I go too fast at any point, when you're watching this on YouTube, in the bottom right of the actual video, there's a little wheel, that's the settings. You can go under that, and you can change the playback speed. You can slow it down to 0.75 or 0.5. So if I'm talking too fast and I'm just blah, 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 you can slow it down and get me at a better pace. You also have the rewind ability. Use it wisely. All right, D, the integral of. Now this is where we're going to get a little weirder, and this is why I said typically, not every time. This is going to be the natural log of x in parentheses squared, then over x dx. Now, I'm writing the dx in the top of the fraction. It could be to the side as a multiplier. It works either way, but I will write it this way. The integral of the natural log of x all squared. So that 2 is not part of the x, and it cannot be made as a coefficient. You cannot bring the 2 out as a coefficient. This is not that classic problem because it's outside. If the 2 is here, then you could bring it out as a coefficient. That's the major difference there. So let's scroll back up, and we said, where did I write it? Here it is, hint. The substitution is usually the inside or the bottom, and if there's a lot of stuff in the bottom, it's the inside of the bottom. Usually does not mean every time. All right, so here, I mean, you've got a top and a bottom, so what should the u be? Should the u, and I'm going to erase this in a second, be the x, or should the u be the ln of the x, or should it be the ln of x all squared? Well, the last case is the least likely because that's the inside and the outside. Typically, that's not how we do a substitution. So that's definitely not it. So is the u the x or the natural log of x? Well, let's do this wrong. And again, I'm going to erase this in a minute. This is going to be wrong. If you let u be x, then du over dx, the derivative is 1. Multiply both sides by dx, and you get du equals dx. So this right here will turn into a u. This right here will turn into a du. But this right here is going to be stuck and it won't go away. So that's clearly a bad substitution. So we did that wrong. So we say it's probably the u equals the natural log of x. It's probably the other one out of that. We gave a reason why the last one was garbage. We just showed why the first one is garbage. So let's let u be the natural log of x. And let's see what happens. So we're going to let u equal the natural log of x. So what that says is the derivative is 1 over x. You've got to remember your 4 or 5 basic differential rules. You never get to forget them. The derivative of a natural log is 1 over x. In this chapter, we've been saying that the integral of 1 over x is the natural log of the absolute value. We didn't need the absolute value for the derivative. So that's pivotal. Multiply both sides by dx. Now, some people might say, well, just flip this. And yeah, that technically works here, but it's too generalized. So let's multiply by dx to get rid of them on the left, which will give us just du is on the left equals, and now this is dx over x on the right. Now, I've been saying so far divide both sides by what's paired with dx, but this is actually a division. So think about your basic algebra. Don't divide this time. Multiply both sides by the x. That way, that x will cancel with that one. And what we end up with is x times du is equal to dx. This is what we need to see. It's solve for dx. So what we do now is we plug the let statement in. Instead of writing any natural logs of x's, we write u. And instead of writing dx, we're going to write x du. Those are the two things we're plugging in. So our integral becomes, here's the integral symbol. Instead of writing natural log, we write u. So this is u. And I said I'd do the substitutions in blue. So u, the square is still there. I don't really need the parentheses anymore, though. Then over, the x is still there for now. The dx gets replaced. What is dx? It's x times du. So this is times x du. And look at that. Holy cow, the x's cancel. Gone. Gone. They're different colors, though, so I don't want to show the slashing. So this is now just the integral of u squared du. Perfect. I don't know why I care that they're different colors. That's silly. I did it before. That's a terrible crossout. The integral of u squared, just add 1 and divide by the same power. So that's u cubed over 3. Don't forget your plus a c. But then we go back to x's. So instead of writing u, we write the natural log of x. So this is parentheses, and you need this parentheses. Natural log of x all cubed, because without the parentheses, it's implying something very different. All over 3, and then a plus c. And boom, there's our integration. Pause if you still need to think about this. E, the integral. All right, big fraction, x cubed plus x squared, all over, parentheses, 3x to the 4th plus 4x to the 3rd squared. And then I'll put my dx to the side. Or I could wrap the top in parentheses and put it in the top. That would be fine as well. So this looks like an integration of a quotient. Probably need a let u equals. What do we let u be? There's a top and a bottom now. So is it the top or is it the bottom? Well, more often than not, and notice I'm not saying every time, more often than not, when you got a top and a bottom, u is typically going to go with the bottom. But we showed you why it failed last time. And it's okay to fail. You get back up and then you try something different. You don't just stare and let an hour or two go by. So let me spoil this. Write this down, even though I'm not writing it down. Whenever there's a natural log involved with integration, that is usually the substitution. I'm lying. I'm going to write it. Usually, more usuallys, if there's an ln of x
in your integral let u equal the natural log of the x, or whatever it is. The reason being, excuse me, is you're gonna, when you do it that way, the derivative is gonna be 1 over x, which means the dx will be x du, and then it can cancel with an x that's in the bottom. Now the natural log could have been in the bottom as well, but you still needed that x in the bottom to cancel in the dx factor. All right, so if you let u be the x cubed plus x squared, that says the derivative would be 3x squared plus 2x, and I don't see anything remotely like that anywhere, so that's probably not going to help. And I also said that with polynomials, you usually need to let it be the higher part as well, the higher polynomials. So let's go with the 3, oops, wrong color, 3x to the 4th plus 4x to the 3rd. Not just the first term, you need it to be the entire inside. So that will say that du over dx is equal to, drop the 4 out in front, multiplied by the 3, 4 times 3 is 12. And then decrease the exponent by 1. Again, that was 4 times 3 times x cubed, the 4 times 3 is 12. Then plus, drop this 3 out front, so it's 3 times 4 times x squared, but the 3 times 4 is also 12. So 12x squared, that's kind of nice, believe it or not. Now what we got to do is multiply both sides by dx. So du over dx equals the 12x cubed plus 12x squared. We're going to multiply both sides by dx. Because of the multiple terms, you got to wrap it in parentheses. Your dx's cancel. So what we get is du is equal to, per the parentheses, 12x cubed plus 12x squared dx. Then we divide both sides by the parentheses to solve it for dx. I'm going to have to squish this in here, so I think you get the idea. I'm dividing by the parentheses so that the parentheses will cancel, giving us that du over parentheses 12x cubed plus 12x squared. That doesn't look like a 3 now, but it is. 12x cubed plus 12x squared equals dx. Honestly, the parentheses is unnecessary here because there's nothing else going on in the bottom, so I can't erase it, but you could leave it if you like. Pardon me. All right. So our original integral, what are we replacing? This inside of the parentheses becomes a u. This dx becomes this du over 12x cubed, blah, blah, blah. Those are the replacements we're going to see. So what we get is the integral. I'm leaving the x cubed plus the x squared in the top alone for now. Over. Then the parentheses, the inside of that is now just u. So because it's just a single term, I don't need the parentheses anymore. So that's u squared, and I said I would change colors to show the substitutions. So that's what changed. And now the dx is now this thing, this du over blah, blah, blah. So this is times du over the 12x cubed plus 12x squared. Okay, so x cubed plus x squared in the top, 12x cubed plus 12x squared in the bottom, they don't cancel each other out. The x's don't cancel, do they? Not yet. But what you can note is, in this bottom here, there's a GCF of 12. Pop that out and see what happens. So we get the integral of x cubed plus x squared over u squared times du over 12 times x cubed plus x squared. Now they cancel. That matches exactly that parentheses. So all your x's are, what's going on? All your x's cancel. So you have the integral of 1 over u squared times du over 12, which is just the integral of du over 12u squared. Or you can rewrite that as the integral, oops, of 1/12 times the integral of du over u squared. Some people don't mind having the 12 in the bottom in the integrand. Some people like to pull it out. It's up to you. It's one and the same. I don't care.
Well, that u is in the bottom, so we need to bring it to the top. So this is 1 over 12 times the integral of u to the negative 2 du. And then we add 1 and divide by the same power to actually integrate. So this is 1/12 times u to the negative 1 divided by negative 1 plus our c. Let's just make that a negative 12 in the bottom. In fact, let's just pull a negative in front of the whole thing. So negative u to the negative 1 over 12 plus c. Let's bring the u to the negative 1 to the bottom. So this is negative 1 over 12 times u to the first. I will write the 1 here for clarity, plus the c. But we got to go back to x's. So final answer, negative fraction 1 over 12 parentheses. We said that the u was 3x to the fourth plus 4x cubed. So 3x to the fourth plus 4x to the third. Now I don't really need to write that 1, but I do need the parentheses because of the 12 in front of it, and then we have our plus c, and that's our answer. Yes, the negative could just be in front of the 12. Yes, the negative could be in front of the 1. Yes, the negative can be in front of the whole fraction. There's 3 good answers for how this can be written. This is my favorite version of it. So this one was a little more involved. There was a little more going on, mainly because of the GCF and having to pull it out, as well as we hadn't seen one of these in class in a couple of days where the u was in the bottom. You had to bring it to the top. Negative exponents, bring it back to the bottom after the fact. You had to be careful, make sure that wasn't just a 1, because that would have been an integration where you get a natural log of an absolute value. All that stuff will continue to be in play. All right. So let's move on. Same topic, but moving on a little bit. What do you mean a little bit? Every single one we've done so far, all 5 of these, have been definite integrals. I'm sorry, indefinite integrals. We're about to get to definite. So far, these have all been indefinite integrals, which means you need a c in the answer unless they give you an initial condition to match. Then you can actually algebraically find the c. We've done that. But for definite integrals, when we're doing the substitution technique, not only do we have to make sure that all of the x's turn into u somehow, that we don't have any x's available, you will have endpoints. The original endpoints are in terms of x. You should, because it's the best process. Now, notice I'm saying should. There is a way to do this without what I'm about to say, but I'm going to emphasize doing it this way. Because if you don't do it this way, it plays a little differently. So you should convert the endpoints to values of u, i.e., plug in the upper and lower bounds, the let statement to get the equivalent u value. So when I tell you to integrate from 0 to 5, those are in dollars. When you say let u equals blah, 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 you're going to yen. $0 and $5 are not the same thing in yen. It's roughly like what, every penny is a yen? And again, roughly. So integrating from 0 to 5 in terms of x, in terms of dollars, when we switch over to u, we're probably integrating from something like 0 to 500. So the upper and the lower limits will generally change. Now, they don't have to. Notice I said, $0 is 0 yen, so that conversion would be obvious. But again, typically, the upper and the lower limits have the ability to change. Maybe both of them change, maybe only one of them changes. But you're changing what we call variable spaces. We're changing dimensions. And it's a lot fancier than how we really treat it. So this is the way you're supposed to do things. Now, notice I said supposed to, should, best, because there is a way to do this without changing. And basically what you do is you just go back to x's and then plug in the x values. But by changing to u values, we're never going to have to go back to x's. We can plug in terms of u's, which is generally a simpler looking equation or function. So let's try this out. Example 3.
And that's where we're going to pause and take our break. It's 7:58, so let's come back at 8:07. All right, and we're back at it with example 3. Evaluate definite integrals. A. We're going to do the integral from 0 to 1 of x over x squared plus 1 dx. And again, the dx go to the side or in the top with that regular x. That's x squared plus 1. All right, so this looks like a quotient. We don't know how to handle quotients, so we're going to do substitution. Let's come in and say let u equals. All right, there's a top and a bottom, so it usually is the bottom unless there's a natural log somewhere. Also, the bottom has an x squared, the top has an x, so yeah, it's probably x squared plus 1. So that would say that du dx, the derivative, would be 2x. The derivative of 1 is nothing. Multiply both sides by dx. I'm going to stop showing the basic linear algebra here. You get du equals 2x dx. Divide both sides by 2x, and you get du over 2x is equal to dx. Again, I'm going to stop showing that basic linear algebra. So the two things we're plugging in, we're going to be writing a u instead of x squared plus 1, and we're going to be writing du over 2x instead of dx. So this integral becomes the integral from, and I'm going to write a to b, because for now, I don't know what they are. We'll get to that in a second. I could go ahead and do this, but I want to go ahead and get the integral set up at least. So the x stays. That x in the top stays. I haven't said to change that. But the x squared plus 1 in the bottom becomes just a regular old u. And then the dx to the side, this dx is now du over 2x. So that's times du over 2x. And look at that. You got an x in the top and x in the bottom. They will cancel each other out. Oh, you're stuck with the 2. Oh, well. So equals the integral from a to b. Now, there's a 2 and a u in the bottom and a du in the top, so you can do du over 2u. My personal opinion, I like to pull constant multipliers out of the integration. So this is a half times the integral from a to b of du over u. But what is a equal to? What is b equal to? You got to plug the 0 and the 1 into the let statement to find that out. So when x equals 0, this is the bottom one. When x equals 0, you're going to plug that into the u equals x squared plus 1. We're plugging into x. So u equals 0 squared plus 1, which is 1. So when x equals 0, that's equivalent to saying that u is equal to 1. When we've changed spaces, when we've changed variables, when we've changed dimensions, when we change from dollars to yen, 0 in x is equivalent to 1 in u. Obviously, that wouldn't make sense for a currency, but again, this isn't a currency exchange. What about when the x was 1? That's the upper limit. What's the equivalent in the u space? That was weird. There we go. U is equal to 1 squared plus 1, which is 1 plus 1, and that's 2. So when x is 1, u is equal to 2. This is the a and the b, the upper and lower limits. So this is the integral, 1/2 the integral from 1 to 2 of du over u. So going from 0 to 1 in terms of x's is the same thing as going from 1 to 2 in u's. There's no x's anywhere, everything's in the same space, so we can now integrate. With a u in the bottom, that's that special case, that the exponents of 1, bring it to the top's a -1, adding 1 to that makes it a 0, can't have a denominator of 0. So this was the natural log rule. Leave the 1/2 alone. The integral of du over u is the natural log of the absolute value of u. And then we're integrating this from 1 to 2. Now we don't go back to x. That's the major difference here. Because we have the values in terms of our new currency, our new dimension, our new variable,
we don't even need the x's anymore. We're just going to plug in the 2 and the 1 into this. And if you don't trust me, I'll show you that it works after the fact. So equals 1/2 times the natural log of the absolute value of 2. So that's plugging in the upper limit. Then a minus, and now we plug in the lower limit of a 1. 1/2 the natural log of the absolute value of 1. Clearly, we don't need these absolute values. So that's 1/2 natural log of 2 minus 1/2 natural log of 1. Please remember that the natural log of 1 is 0. You are supposed to have that memorized. The natural log of 1 is 0. So this is equal to 1/2 the natural log of 2 minus 1/2 times 0, which is just 1/2 natural log of 2. Please note that this is the same thing as the natural log of 2 raised to the 1/2, which is the same thing as the natural log of the square root of 2. They're all the same. But you're probably just going to stop at the 1/2 natural log of 2 in this course. Remember, coefficients can be brought up as exponents inside of a natural log, and then a fraction exponent is just a radical. All right, so in green, I'm going to show the alternative way. The way that I will never do again. So this is when I said you should convert the endpoints. You don't have to. Here is how you can do it without converting the endpoints. We had our integral from 0 to 1 of, what was this? X over x squared plus 1 dx. We still said let u equal x squared plus 1, and it ended up giving us that dx was equal to du over 2x. Those are the two things we plugged in. So now our integral is from a to b, and it's just du over u. I'm saying a and b, I'm not saying 0 and 1. If I write 0 and 1 here, it's wrong. I don't know what the a and b are, and I'm not going to find it. Do the integration. That's the absolute value of the natural. I forgot my 1 over 2 in the front. Sorry about that. So that's 1/2 the natural log of the absolute value of u, evaluated from a to b. Now, because I never found the u values, we go back to x. So this is 1/2 the natural log of, instead of writing u, we write x squared plus 1. So absolute value of x squared plus 1. And we're evaluating this from 0 to 1. See, I don't use 1 and 2, I use 0 and 1 because now I'm back in x's. Your numbers have to match the variable space. So this is 1/2 natural log absolute value of 1 squared plus 1 minus 1/2 natural log absolute value of 0 squared plus 1. 1 squared is 1, 1 plus 1 is 2, the absolute value of 2 is 2, so that's 1/2 natural log of 2 minus 0 squared plus 1 is 1, that's minus 1/2 natural log of 1, which we already know is 0, and you get your same 1/2 natural log of 2. Now you might say, Mr. Beckner, I think that way's easier, and if you do, then you can use it, and that's okay, but trust me, there are times when it isn't. It depends on how simple or complicated your let statement is, and how simple or ugly your endpoints are. I personally think more often than not, it's easiest and better to do the change here, because then that way you can see the numbers under the new variable. Because what a lot of students will do that try to use this method is, instead of writing a and b here, guess what they do? They write 0 and 1, then they end up plugging the 0 and the 1 into this one, and they will not get the appropriate answer. So they just go, oh, we'll go ahead and plug the 0 and 1. No, you never found out what it was equivalent in u. So you have to be very, very, very careful with that stuff. All right. I'm doing that. Give me a second. I thought I had another problem and I'm not seeing it. Actually, give me like 20 seconds. It's really weird. Now when I think I said this last time, but now when I hit mute, it gives me this scary, like, I have to confirm recording again. And now I'm terrified that I'm going to miss it because of what happened in my other class. I mean, I didn't do anything wrong in my other class. I'm just terrified of something not recording now. That was Zoom messing me up. All right, so let's try this out with a word problem. Example, I think we're up to 4. Pollution is being discharged like rate of R of t is equal to word rate. That probably means we're going to do a derivative, right? 400 e to the, 400 t, I missed my t. 400 t e to the t squared. Ooh, that looks like a familiar format. And then that's in tons. Per year. T is the number of years. Let's measurement begin. Find the total amount of pollution discharged to the lake in the first 2 years. So I gave you a rate of something happening and we want the total. We have said multiple times that when you're given a rate and asked for a total, that's accumulation basically, you're integrating it. So what we have to do is the integral from 0 to 2, first 2 years, of 400 t e to the t squared dt. Well, we're going to need a substitution. We're going to say let u, and we've basically done this already, be t squared. So du dt is 2t, which means du is equal to 2t dt, which means that du over 2t is equal to dt. So that gives us the things that we need to change. So it's the integral from a to b now of 400 t e to the t squared is now u, e to the u, and then the dt becomes du over 2t. Well, the 400 divided by the 2 makes a 200, so this is the integral from a to b of 200, and the t's will cancel, so this is just e to the u du. But we got to find the a and the b. We got to find the upper and lower limits. So when t is equal to 0, that's year 0, plugging that in the let statement, u would be 0 squared, which is also 0. So that's the a. When t is equal to 2, your u is 2 squared, which is 4, so that's the b. So this is the integral from 0 to 4 now, not 0 to 2, of 200 e to the u du. If you like pulling out the 200, be my guest. I really only mainly focus on doing it when it's a fraction part, but it's still cool to do it this way. 0 to 4, e to the u du. The integral of e to the u is e to the u. We don't need a plus c because it's a definite integral. So 200 e to the u evaluated between 0 and 4. So this is 200 times e to the 4th power minus 200 times e to the 0th power. And remember, anything to the 0 is 1. So this is just 200 times e to the 4th minus 200 times 1. Just 200 e to the 4th minus 200. Now there's your analytic answer. But of course, this is an application, so we probably want to approximate this by jamming it into a calculator. So we get our calculator. This was some stuff from my last class. 200 e with an exponent to the 4th power, close the parentheses, minus 200. Make sure you know how to type all this stuff in your calculator. And you get 10,719.63. And we're going to round this to the nearest whole. So this will be 10,720. So that would be in tons of pollutant. Sounds terrible. So calculator, let's graph the original function to show you what we're representing. We had 400, I got to use x instead of t, and then times e to the x squared. Oops, e to the x squared. Close it, close it. Let's start out with a standard zoom and see what we get. Well, we don't even really see anything. The reason being, there's a 400 up there, so we probably need to make this window. In terms of the y values, we only need to go 0 to 2. So y minimum, 0, y maximum, 2. I'm sorry, those are the x's, not the y's. Bah. 0 to 2 for the x's. The y's, we definitely don't need any negatives, so 0, maximum. Well, that's probably going to be some big number. Let's try 10,000. Well, the total of it was 10,700, 200, so let's try 20,000 to start off. Let's see what we get. And you can see that this thing even still grows way beyond what I've got. If I hit trace and type in 2, we get 43,678. So let's go to 45,000. The program runs a lot slower than I can do this by hand. And you can see your exponential curve, the explosion taking off, because this pollutant just keeps dumping in at an accelerated rate. Hopefully somebody stops it at some point. So this was the growth rate. So at any point along this curve, that's how quickly the pollutant is going in at a changing speed. So integrating this, getting the area under the curve, would give you the total pollutant over that amount of time. So if we go second, calc, option 7, lower limit of 0, enter, upper limit of 2, because this is not in U's, this is in X's. So big numbers, it's going to take a minute to calculate. Yeah, 10,719.63. Same answer. So that's the total pollutant. Again, when you're given a rate and asked for a total, you are integrating. When you are giving a rate, and it might not even say the word rate, you might just need to use clues like the word per is in there. That's a rate. Or a number of years since. That's another thing that might denote a rate. Doesn't always, that last bit, but it can. All right. So that will close out .5, integration by substitution. And I believe the last section we're going to cover from chapter 4 is 4.6. I'm confirming that real quick. Yeah, 4.7 is on numerical integration. That's more of that stuff like from 4.2 where we had the rectangle rule, and I said there's also a few others like a trapezoid rule. There's also something known as Simpson's rule, which we're not going to get into that, but there are many different ways besides just rectangles for doing numerical integration, for approximating the area under a curve. And again, in this course, we want to focus on the analytic methods because we're not really teaching you how to do a bunch of computer programming and spreadsheets and stuff like that in here. All right, so save. Please don't crash. Please don't crash. All right, new. So last section of chapter 4, not necessarily the last section of the next test though. Again, we'll talk about that more next class. 4.6, integration by parts. Let me tell you, this is not the easiest method. Sorry, where'd my page go? Here we are. Integration by parts. So this is another scenario for integrations that feel like products, quotients, chain rules. However, sometimes it's needed
really simple looking integrals that don't follow previous rules. Lots of space. Oh yeah, Word's about to crash. I love technology. There's not even a title up here. I can't change the maximizing. I wish it would just go ahead and crash. Let me copy paste this. Maybe I can force it to crash. That's me clicking heavily. I really don't have time to waste. Thank you, technology. Are we having fun? All right. Okay. Let's try this again. Oh, that's not good. Sorry, I want to make sure that I don't file saved. All right, it did. What did I just do? Darn it. I didn't mean to close the whole thing. And what? No, it's not there. Oh my Lord. Oh my Lord. All right. 4.6. Sorry, I'm frustrated. Integration by parts. This technique is another. This is going to be paraphrased because I didn't have this written down. I always just fly from the hip. Is another technique used when it looks like a product, quotient, or chain rule. Sometimes it's used for simple looking integrations that don't follow previous formulas. What we're going to do is we're going to do the proof of this. This is one that I feel like is necessary to do, and it's not the prettiest thing in the world, but we're going to do it. So let's borrow product rule derivatives in the following form, ultimately solve it for, there's two things you can solve for, but one of the, hold on, I'm trying to say too many things at once. Let's borrow the product rule for derivatives in the following form and integrate it. Then solve for one of the resulting integrals. So the product rule states for derivatives that if you have something written as a product, and I'm going to use the letters U and V because that's what the letters are going to be seen in this. It's because it kind of feels like a substitution, but it's kind of not. So the derivative, this is me saying the derivative of a product. So that's the derivative symbol of a product. It's, and we've been saying it's the derivative of the first times the second plus
the first times the derivative of the second. And we've said there's like 16 different ways to write that. That's the one I'm going with. Let's integrate both sides. Integrate this. Over dx, which was the original variable. I'm not going to be able to fit that in. Whenever you have a derivative of something, a derivative of something equal to something else, if you integrate it, you get the regular function. So what we're doing, we're taking that black handwritten stuff, and we're just going to integrate both sides. Now, when you integrate, you have to throw in that dx, whatever variable you're integrating over, because we're not going to see u's and v's in the problem, we're going to see x's. So the left side is the integral of u v prime times dx. The right side is the integral of u prime v plus u v prime all over dx. Again, all I did was I took this right here and I integrated both sides. Whatever you do to one side, you do to the other. That's a rule of algebra, right? You can take a derivative of both sides, you can integrate both sides, and we've done this before. Now, please note that when I write u prime, that is really du over dx in differential format. And when we write v prime, that's really dv over dx. Because we're going to need this notation to kind of clean this up. So all the primes, I'm going to do a replacement. So this becomes the right-hand side. Hold on, I don't want to write just the right-hand side. I want to write the left side. The integral, and it's no longer an integral, blah. Because we're integrating a derivative, the integration of a derivative is itself. There's no product rule needed because this was the derivative of a product. So the integral of a derivative is itself. The left side is just u times v. Since I've changed something, I'll switch colors. We integrated the left side to get that. Equals. Now on the right side, where I see u prime, I'm going to write du over dx. When I see v prime, I'm going to write dv over dx. So integral, parentheses, u prime, blue for changing. So that's du over dx times v. And then plus u times v prime, that's really dv dx. And then there's our parentheses closing and the dx. Let's let's make this two separate integrals. Let's separate the right-hand side. Separate, abbreviated, the right-hand side. So what we'll get is, now I'm not changing the left, so I'm going back to red. uv equals integral of, I don't need the parentheses anymore, I'm just distributing the dx. I'm just giving the dx to both of these bits. That's all we're really doing, and we're going to make it two integrals. So this is now the integral of du over dx times v times dx. Again, this dx has been given to the first term. Now, since I've got my dx, I close the integral. So we go plus integral u times dv over dx dx. Again, the main thing that's really happened here was I distributed the dx, and now that I have it distributed, I make it two separate integrals. Well, look at this. You got a dx in the top and bottom. You got a dx in the top and bottom. You can cancel the dx's. So now what we get is uv equals again, I'm canceling the dx's. Those are gone, and those are gone. So the integral of duv, which is a weird format, du times v specifically, plus the integral of u dv. I'm just going to swap the order in the first. So what we get is uv equals the integral of v du plus the integral of u dv. Now what we do is we're going to subtract one of these two things. It technically doesn't matter. We're going to subtract the integral of v du though. This is just how most mathematicians do it. We're going to subtract the first one. So we're going to subtract minus integral of v du minus integral v du. What this gives us is uv minus the integral of v du is equal to the integral of u dv. All I'm going to do is swap the order of the left and the right side. So what we get is the right side, integral of u dv is equal to uv minus the integral of v du. This is a formula for integration by parts. This involves two substitutions and some extra stuff. Some extra stuff. Oh no, when I made a new page, I didn't hit enter 10 million times. Fudge. Okay, for some reason hit enter didn't push everything down. I really have a hard time predicting how Word is going to work sometimes. Because sometimes when I hit enter, it makes all that stuff go down. It's weird, it's wacky, it's wonderful. All right, so this is going to involve two substitutions. We'll have a let u equals blah, 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 blah. And we will have a let dv equals blah, 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 blah. You will need to take the derivative of u and solve it for du. Then you'll integrate dv to get v. This problem is all over the place. That's why I'm just going ahead and flat out putting the techniques up front before we start doing anything. And I think we'll get to one of these today. So what in the world is this formula, the integral of udv? But Mr. Beckner, you said these variables had to match. That's kind of the point. Now, your original problem is all going to be an x, but you're going to do two different substitutions. One of them is going to be a u, and one of them is going to be a dv, not a v, a dv. And then for the u, you're going to take its derivative, and instead of solving it for dx, you'll solve it for du, because the du is part of the formula. It's not a dx, it's going to clean up things. And in this formula, you also need v, and the way we get v is by taking the dv part and integrating it. What this formula, again, enables us to do is integrate products, quotients, chain rules that don't work under a normal substitution, but might work with this advanced technique that involves a derivative and an integral and then another integral. The reason it's called integration by parts is this first term, this first part, is already integrated for you. There's nothing else you'll have to do. You just plug in whatever u is and whatever v is. In the u, you will make the statement, let u be this. The v you'll find after you make your let dv statement and integrate it. But this last part is not automatic. You'll have to plug in the v and the du and then integrate that. So again, part of this initial process will involve a derivative and an integral. You plug things in here, and then you will actually end up integrating part of it. Again, this first part does not have an integral. The second part does. This, again, is typically used when substitution fails. This is generally used when a basic substitution technique fails. So if you were approaching a problem and you said, I don't know what to do, what should I do? And you've got a list of options, I would try a regular substitution first, and then I would try integration by parts. What integration by parts is good for is when what you have, you don't know how to integrate, a substitution doesn't help it. But maybe if you do this weird thing, maybe this new integral will actually be significantly easier. That's what we're hoping. We're hoping that we'll turn an integral that we have no idea how to handle into part of something that's already been handled for us, and then another part that'll be much simpler. So let's do one example. Let's try this out. Make sure I got lots of enters here for later. Example 1, integrate. I'm just gonna, how do I want to have this set up? I'm going to copy this, just put it here, and then remind us what the formula is. That the integral of udv is equal to uv minus the integral of v du. It's kind of got this bounciness to it. udv, the other integral is v du. It swaps them. This right here is just the product of the u and the v. You have to memorize this. That is supposed to be memorized. So for example 1, A. We have the integral of x times e to the x dx. Mr. Beckner, we did that with substitution last time. No, we didn't. That was e to the x squared. The irony is, the simpler exponent makes this problem much worse. If you try a normal substitution, you'd let u be the x. Taking the derivative would be a 1, and there'd be nothing to cancel this x down here. So that says, nope, we need to go to this other technique. So here's one of my flares, as I like to say, my warning signals that substitution is going to fail. This and this are not off by a power of 1. That's usually what happens in a product. Now, if it was a quotient, that's not necessarily the case, and we have seen an example that way. But that's what says the normal substitution technique is probably going to fail. And let me be honest, for like a third of the problems that end up needing to be done by parts, I would try substitution first, I would hit a dead end, and then I'd go back to integration by parts, or go forward to integration by parts. So these are the two lets we make. We say let u equal, and I'm going to make a statement about what should be what ultimately. This one is set up in a more proper format. The u needs to be the x. And then we're going to say let the dv be everything else. So I'm going to write this part down after trying an example. So let dv be everything else, the e to the x dx. The dv has to have the dx. That is 100% of the time, because when you go to integrate it, you need both of those differentials there. So for the u, we said we take a derivative. You will need to take the derivative of u. What in the world? Select. You will need to take the derivative of u and solve it for du. Then you'll need to integrate dv and solve for v. So let me just make sure I copy paste that there too. So take the derivative of the red part. So du dx equals, well, the derivative of x is 1. Solve this for du, so multiply both sides by dx. You'll get du is equal to 1 times dx, which is solved for du. Du equals dx. This means they're changing at the same rate. It's an interesting scenario. This is what we're going to need along with this. Now for the dv equals e to the x dx, you integrate both sides. Integrate dv, integrate e to the x dx. Integrating a differential just gives you that variable, so the integral of dv is v equals, and the integral of e to the x is e to the x. Skip the plus c part for this. Right here, we're just going to put the plus c at the very end of the problem. So in this part, what we need is the dv is equal to blah, 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 and what the v is equal to blah, blah, blah. Those are the 4 bits we need to plug into this formula. Now we're not plugging anything into the left side. The left side, the x was the u, the e to the x dx was the dv. So this is the integral of x e to the x dx. That should now be equal to formula u times v. Here's your u, here's your v. Multiply them. But don't write u and v, write the things in terms of x's. So x times e to the x. Again, this right here is the uv from the formula. The u, we made the statement about, but the v, we had to integrate the second statement to get it. Then there's a minus, then there's an integral symbol, and this goes v times du. So v times du. What's interesting is you don't plug in the dv into the right side of the formula. It's just necessary for the left side. So you don't even end up using this part for the plugging in. It was just critical at the beginning. I don't even necessarily need that circle because of that. So minus the integral of v du. The v was here, so that's e to the x. And then the du, that was this, which is just dx. U v minus integral v du. And the good thing is the integral that we're left with is simple and we know how to handle it. That's the point of integration by parts. We didn't know how to handle x e to the x, but we do know how to handle e to the x. So this becomes x times e to the x minus. Integrating e to the x is literally e to the x. Now we did the integration in the problem, so we put our plus c, and guess what? That's all you can do with it. That's the answer. So again, how did we use this? We say let u be the spoilers. It's generally simpler looking part. So when I say simpler, what looks simpler, x or e to the x? X looks simpler. After that, we say let dv be the rest of the problem. After that, we integrate dv to get v. After that, we take the derivative of u, solve for du. Again, there's one major difference between substitution and integration by parts. Substitution, you're solving for dx. Parts, you're solving for du. Just do this. I want this all together, so let's remove the space. Perfect. Special note though. The natural log of x is involved. U is generally the natural log of the x. Typically. Kind of like with the substitution technique, when the natural log was involved, we usually let the u be that. It's the same thing here. So if you have a problem that you think you need to do with integration by parts or substitution, and it's got a natural log somewhere, the u probably needs to be the natural log of x. Again, I said typically, there's exceptions to every rule, but this is what you would expect in homework tests. All right, so I do need to start getting ready. All
right, last stretch. Here we go with b.
Let's do the integral of x cubed times the natural log of x dx. So if you try to do substitution, there's a natural log, so you'd set let u be the natural log of x. Its derivative would be 1 over x. Then when you solve that for dx, you would get du over x. And then when you plug that in, you would have an x in the bottom and you'd lose one of the x's here. So this x cubed would go down to an x squared, but now you'd have an x squared here and a u here, and that will fail because you can't have mixed variables and integrate this way. So substitution technique would fail here, as just verbally described. So we got to step it up to this integration by parts. And again, that formula is the integral of u dv equals uv minus the integral of v du. Third time I put it on the screen because it's so important. So we'll say let u equal the simpler part. Now, generally you'd say x cubed is simpler, but I made that little special 3 asterisk memo. If natural log is involved, let u be that. So just trust your teacher and try it out. Let's see if it works. Which makes dv the rest. So this right here was the u, and let me switch colors. So dv has to be everything else besides the integral symbol, so the x cubed and the dx. We take the derivative of the u, we integrate the dv. So du dx, the derivative of the natural log of x is 1 over x. That's a formula you should still have memorized. You never get to forget any formula from this class ever. Sorry to say. And then we want to solve this thing for du. Again, this is the slight variation of the substitution technique. We're going to solve this for du, not dx. So I just got to multiply both sides by dx. Oh, that is awful. Let's not do that. So dx on the left, dx on the right, so that those will cancel. And you end up with du equals dx over x. And actually, I said something wrong earlier. I said that the x cubed would cancel. If you solve that for dx, the x goes on that side and actually stacks up to the x to the fourth. It gets worse. Sorry about that. Either way, the point was it did work. So now what we get is du equals dx over x. If you want to leave that as 1 over x times dx, you can. I'm just compressing it. So the dv, we're going to integrate. Whatever you do to one side, do to the other. And we like these separated because there's no funny business. There's no mixture of variables. This is actually called separation of variables. It's a fancier name for a fancier technique, but this is just a lower version of it. Integrating 1 just gives you that variable, so that's a v. Integrating x cubed gives you x to the 4th over 4. So those are the things we need. We need the du, we need the v, and we also need the u. Those are the 3 things that get plugged in. We don't actually plug in dv. dv was just necessary to get to where we're going. It's 3 of these 4 that get plugged in. So what we now get, the integral of x cubed times the natural log of x dx, which we're now calling the integral of udv. This is now equal to u times v. The u is the natural log of x times v. V was x to the 4th over 4. I'm using color this time to at least show if it came from a u or a v. So again, that was uv. Then we have a minus and an integral. And this will be v du. So we're going to use the v again. So there's an x to the 4th. I'm sorry, that should be blue. X to the 4th over 4. So that's the v, and then times the du. Du was dx over x. So let's clean this up some. First of all, the natural log of x times x to the fourth is not the natural log of x to the fifth, because this x counts as inside, the x to the fourth outside. It's actually better to write the x to the fourth first. So all in one color now, that's x to the fourth times the natural log of x all over 4 minus integral. I'm going to bring this 4 out front, so that's a 1/4, then my integral. Again, this 4 in the bottom is now just out front of it because it won't have any effect. And then we add 4 x's in the top, 1 in the bottom. You'll lose one of them, so we got x cubed dx. So this first bit has already been integrated. There's no integration symbol there. Do not integrate it. You can't integrate it. In fact, it is worse than the original problem. But that's okay because we don't need to mess with it. But what we can integrate is this bit right here, and it's an extremely simple power rule, which the original problem was not. That's what parts does for us. It gets this kind of ugly bit out of the way, which we take with a leap of faith. I mean, again, we prove the formula, so it's not really a leap of faith, but if you don't follow the proof, then it might feel like a leap of faith. But it is just, it takes the product rule of derivatives and integrates it and rearranges it is all it is. You might say, well, why didn't do the quotient rule? Maybe there's a method out there that involves that. Maybe you're glad we don't use it. Okay, so integrating x to the third, well, we literally already did that earlier, and that's what's also funny, integration by parts. Very often you get 2 of the same integration, so you should really know that. All right, so x to the 4th, natural log of x all over 4, minus, here's our 1/4. Integrating x cubed gives us x to the 4th over 4. That's times. And then we integrated, so here's our plus c. 4 times 4 is 16. So this would be x to the 4th, the natural log of x over 4, minus x to the 4th over 16 plus c. That is one way of writing it. If you prefer to have the fractions out front, you can always do that. So 1/4 times x to the 4th, natural log of x, minus 1/16 times x to the 4th plus c. Same answer. Neither I nor my math lab care which way you did that. This is the most involved integration technique that we get. I can guarantee that. But it's a good technique. It's a very important technique because in the real world, most integrals are not so clean or clear-cut and dry. I've seen way more problems that look like this in the real world doing actual math, not just from a textbook, versus just integrating x cubed. I'm not saying I haven't seen plenty of these x cubed. I'm saying I've seen a lot more things that look like this. Because in real world dynamics, things are much more complicated. So that was an example where we let u be, which you might not say is the simpler part, but it's got that special case. Now, what if you try to do that the other way? What if you would try to do this? And let's pick a terrible color. I like red for wrong, but I use red so much I can't really do this. So what if, I'm going to do this kind of small. Oh, sorry about that. I hope that wasn't too loud. I tried to reach for the mute button in time, but I failed. All right, so here's our original integral, the x cubed natural log of x. What if you did this the other way? So what if you said, let u be the x cubed, and you said, let dv be everything else, which would be the natural log of x dx. Now, this is not a typical substitution. Well, I don't want to say that. You might say, well, just let u be the x, not the x cubed, because back in the substitution technique, you usually let u be the inside. Well, this time the inside isn't like a sum or difference of a bunch of terms with a bunch of different exponents. It's just x. So that's why I don't just say let u be x. It would literally do nothing for us. So we try x cubed. Again, we're used to seeing problems where it was like 5x squared minus 17x plus 3 raised to the 5th power, and then u would be the thing inside the parentheses. This is a very different problem. Okay, so take the derivative. Du dx is 3x squared. All right, integrate. Integral dv equals integral natural log of x dx. Well, the integral dv is v, and the integral of natural log of x is, well, we haven't given a formula for that. We know that the integral of 1 over x is the natural log of the absolute value of x, but that says nothing about the integral of a natural log of x. Question mark, question mark, question mark, question mark, question mark for now. Now, I'm not saying you can't do this, and in fact, it's literally going to be the next example. But for now, we have been led to an integration that we're questioning and we're not sure of, and I would probably just want this to be its own problem. So that's why I'm trying to demonstrate here that this would be not a great path. And that is the main reason why we generally, when we have a natural log of x, we want that to be the u, because you'll take a derivative of it, and we know the derivative of the natural log super easy, but the integral of natural log, while we can do it, it is a little complicated. So that's why I said not a great path, and it's not a good path at all, but I'm not saying it can't be done, it's just not a good path. All right, C. The integral of the natural log of x dx. So again, I just demonstrated why it's not a great idea to let the dv have a natural log of x. So that gives us a clue here. We probably shouldn't let dv be all of this. So substitution is going to fail. If you let u be natural log of x, the derivative is 1 over x, that x is not going to be able to cancel with anything because there aren't any x's to cancel. So you would actually make this worse by using the substitution technique. You'd get the integral of what, x times u. No idea how to do that. So don't do it that way. Let's try out this other technique. Let's say let u equal something and then let dv be the rest. We've already seen that letting dv be the natural log is a bad idea. So let's try letting u be the natural log of x and dv be everything else, which is literally just dx. Again, calculus can be about trying something and failing miserably, trying something again, and then maybe getting it right, maybe third time, maybe fourth try. But you can't expect in calculus to do everything right the first try, at least as you're doing more expansive problems. All right, derivative of the left side. And I was supposed to do that right in blue. Not a huge deal. So we said let u equal the natural log of x. We said let dv equal dx. Let me just go ahead and integrate the right side so I don't have to keep switching colors. Integrating a differential just gives you the variable. Again, we're really integrating 1, which the integral of 1 is x or v, or whatever letter we're talking about. The left side there's a v, so it's v. The right side there's an x, so it's an x. For the derivative, you get du over dx equals 1 over x. Solve for du, so we multiply both sides by dx, and we get du equals dx over x. It's literally the same as last time, so I'm not going to show the multiplication this time. Now again, we're only going to need 3 of the 4 parts here. We're only going to actually end up needing the du, because that's in the formula. Hold on, give me 10 seconds. Sorry, guys. Okay, so we need the du, we need the v, and we need the u, because the formula has u, v, minus integral of v du. The right side of the formula doesn't have dv anywhere. The dv was just to get rid of the dx, integrate it to get the v. So those are the 3 things we need. So our integral becomes the integral of natural log of x dx becomes integral of, and I'll do my colors perfect this time. So then, why did I write integral? That was the uv. So we, v du. So we have our uv first. The u is the natural log of x times the v is that other x, and again, these will not multiply to make an x squared, minus the integral of v du. So uv minus integral v du. V is the x, then the du was the dx over x. And again, the whole goal of this thing is that this integral ends up simple, one that we know how to compute. And what's cool is it does. So that's x times the natural log of x. I'm just taking the blue one and putting it in front of the red ink. That's all I've done there. Minus the integral of, the x's cancel. That's just the integral of dx. There's a 1 there implied. This is very simple. This is literally the simplest integral you ever get. So that's x times the natural log, x times the natural log of x minus the integral of dx is x. Don't stop there though. Don't forget your c. So what is the integral of the natural log of x? It's x times ln of x minus x. Now, if you were in an advanced calculus class, I have seen this on formula sheets, but you still have to memorize. I don't want to say a formula sheet. I've seen this on integration sheets, but students are expected to memorize those. Regular calculus students have to memorize 20 or 30 of these things, just like they have to memorize 20 or 30 different derivatives. We only have 4, 5, 6 each. We have a much easier job. Sorry, I had to go turn something off. This is not one we expect you to memorize because it's a little wackier. The integral of natural log of x is x natural log of x, then minus x. It's kind of an interesting formula. You can call it a formula and you can memorize that. If you can memorize that, if I gave you this as a test question, you could certainly use that formula. But what I expect my students to do, since I don't say it's a formula, I don't put it on a formula sheet, I expect them to do integration by parts to get this. Now again, if you chose to memorize it, that is your decision. And at one point in my life, I had this memorized. I will admit I don't have it memorized off the top of my head right now, because I just do it by parts. I can do it in about 20 seconds. That's because I've done it a lot. So it's kind of funny. You would never think that this problem, because it's only got one term in it, one bit, you would never think integration by parts would work, because integration by parts is usually used for things that look like products or quotients or chains. This doesn't look like any of them, and yet it works. There are other there are other classifications of functions where this works. And it's not polynomials. So what you could say, all right, we'll go back to the green. Now that we know how to integrate natural log of x, that makes the v this thing. X ln of x minus x plus c, which is kind of ugly. And if you go and plug that into the formula, so this would be minus the integral of v du back up here. So the v is this thing down here. The du is this 3x squared. Do you know how to integrate this black ink times this green ink? Again, going back up here. What you could now say is that this is equal to the original integral is equal to uv, which would be x cubed times x ln of x minus x, ignore the plus c when you're doing that, and then minus the integral of v du. So du is 3x squared, so that's going to be x ln of x minus x times 3x squared dx. What in the world has happened here? That looks atrocious. Now, here is what's interesting. You can integrate it. That is integratable. Because look at this. We did x cubed natural log of x in example B. It required parts. When you distribute this, this term right here is going to end up being 3x cubed natural log of x. So it's just the same answer, but with a 3 in front of it. This last part would be integrating 3x cubed, but again, it's terrible. You already did integration by parts to get to v. Now you're going to have to do it again, as well as there's a lot more to integrate. There's 2 bits to integrate instead of just 1. That's why I didn't say this is wrong. I said it's not a great path.
So yeah, sometimes it's interesting to look at the approach of integration by parts from both sides of things, the good way and the not so good way. I just like doing that here and there. But anyways, we are going to call it for the evening since we only have a couple minutes left. We will finish that material next time, as well as keep charging forward. Not too many classes left. As a reminder, your 4.4 and 4.5 homeworks will be due in a week once we finish those sections. 4.6 will be due the week after once we finish that section officially. Test 3 is going to cover 4.1, 4.2, 4.4, and 4.5. No problems directly coming from 4.3, as we said. And then that's going to require the webcam setup or cell phone camera setup. So make sure that you get something organized. I'm thinking the 12th through the 14th, but again, we will 100% confirm that next class on Monday. So besides that, have a good week, have a good weekend. If you have any questions, shoot me an email. If you have any issues with these particular test dates or with the webcam setup, please email me immediately so we can work on an alternative arrangement for you, like taking it in the testing center at TCC or taking it a day early, whatever we have to work out. All right, so take care, everyone.